Hello, I am Lewis Taylor, and thank you for watching this presentation regarding an in-depth exploration of applying Lean Six Sigma methodologies to the field of AI-driven protein folding prediction and synthetic design for drug development. To stay within the confines of my time limit, and for your convenience, I will provide searchable Wikipedia terms at the bottom of certain slides and provide the URL links in the notes section for the vocab that is outside of the scope of our operation management course. I'm excited to present this topic because I've been thinking about this topic since Module 2, and because of this course, I learned that this issue has personally affected my career for the past 8 years of my life. The bottom line up front. The current application of AI to predict how a specific protein is naturally folded in a three-dimensional space inside an organism is ultimately flawed, and the data produced in the past decade cannot be applied to in vivo applications, such as drug development. The novel concept of applying Lean Six Sigma to protein folding prediction algorithms is slowly being accepted in the protein modeling field. I predict that this will result in either a complete overhaul in existing AI models or some form of progressive retraining of existing models within the next 5 years. This will then allow for correct protein folding predictions and breakthroughs in protein-based medical treatment. I can personally attest that the failure to apply Lean Six Sigma to protein folding AI has cost Roche Pharmaceuticals well over $7.5 billion in a failed investment since 2019. If we do a literature search using the NIH publication search engine, we see this growth of publications regarding AI-based predictions for protein folding. This is partially due to the advent of Google's DeepMind platform being released to the public. Now, if we search for AI protein folding and Lean Six Sigma, we see a huge growth in the last 2 years. This is due to the global start of our course correction. Let's define the issue first. These Fortune 500 companies are paying $500,000 to millions of dollars for a single research contract to use AI products in academic labs to design synthetic proteins necessary for a drug therapeutic strategy. There are many AI models, AlphaFold, Rosetta, DeepMind, and others. Everything looks good until we start the pre-portfolio animal testing and we start getting null to negative results. Just like you buy the Toyota race car, but you get a lemon straight from the factory. I found an engineering thesis through RIT by Nuhad, who identified that we have originally been measuring our prediction accuracy by true positives over all predictions, seeing as that the true negatives and the false negatives are actually thrown out of the prediction system. The crux of the problem is we have been reinforcing our AI using a much older method. We've been using protein crystallography, which requires us to put a protein in its crystallized form, not its solubilized natural form. This would be as if we told the AI to guess what water looks like and then reinforce the idea that water can only be in ice form. The analysis that came from this issue came to light partially due to COVID. With so many eyes looking at the SARS-CoV-2 virus during the pandemic, there's a collective acceptance that we need to start including the concept that proteins have motility in their substructure. Here you can see the fluidity within the SARS-CoV-2 spike. This is the part that injects itself into the target cells. To improve our understanding and modeling of protein folding, we as a society have and will likely increase our dependence on quantum computing for protein modeling and move away from the neural network AI systems. And finally, control by sustaining improvements over time and proving that our models are working within in vivo testing on biomedical applications, rather than fitting them to protein crystal structures. Now, how does this apply to Roche? Well, Roche in 2019 bought Spark Therapeutics because it owned the first and only adeno-associated virus-based gene therapy drug for an inherited disease. This drug was called Luxturna, and it was to treat a very rare form of inherited blindness. The next goal was to treat Usher syndrome using the same platform. The problem was the USH2 protein is massive, and as you can see here, these are the pili in the eye, very similar to the ear structure of how you actually hear. Usher is this little, well, big molecule actually, that's holding your cilia together. So the problem with this is that USH2A is massive. It won't fit in a single virus. So the strategy here was to cut the Usher protein in half. Well, actually, it's the mRNA code for the protein, but still. And we were to cut it in half, and so to insert it into two separate AAV viruses and then inject them side by side. We wanted then to attach these synthetic proteins on both ends of this Usher protein so they literally act like Velcro. So once they're inside the eye, these Velcro pieces will find each other and then attach. We in fact actually called this project the Usher Velcros. We paid over $500,000 to the David Baker Lab to use Rosetta to design these Velcros. For over 2 years, we could never get this to work in animal testing, and it cost us well over $1 million in animal testing alone, and hundreds of lives of sacrificed animals. This led to massive layoffs and downsizing within Spark Therapeutics, to the point that Roche actually shelved all of their AAV-based pre-portfolio projects by 2024. If Lean Six Sigma was applied 5 to 8 years earlier to AI-based protein folding predictions, we may have been able to catch this issue sooner. But academic culture demands publications and data generation, not to identify faults. But we'll never know what could have been. And so my final concluding remark, and why I believe the control portion will require quantum computing rather than admitting to flawed neural network AI models, is because of the culture of academia. Culturally, we don't want to write publications pointing out other people's mistakes. But by using a novel invention, quantum computing, we can go around this issue and start writing publications and performing experiments with this new technology instead. So thank you very much for watching this presentation, and I hope it shined some light and gave you some new ideas to think about regarding Lean Six Sigma. Thank you very much.